Do you think that it is possible to use nanostructures to capture carbon from the atmosphere?
Yes, it is. And indeed, we have also written an article about it, which is the one. And it is possible. And actually, that's been going on for a relatively long time. Like I'd say at least the last 10 years, probably a little bit more. In the last years and last decades, metallic nanoparticles in particular, in this case, have been widely used to capture carbon. Of course, when we say capture carbon, we mean the capture of CO2, carbon dioxide, which of course is very important also for the greenhouse effect. So this is also a topic which has been getting increasing attention and curiosity in general in the last years. So yeah, in general, metallic nanoparticles are very important in this case because based on the precise metal, the precise element that we use as a nanoparticle, we are able to capture carbon and to store it in different compounds. For example, silver, gold, and copper sometimes, and also other elements are able to give us different compounds. In this case, trimetallic nanostructures, they are to be preferred over other nanoparticles. It's just that they are simply different. They're used in a different way and to obtain different compounds. And so yeah, trimetallic nanostructures are an alternative which has become popular in this last year. They represent, yes, an alternative which is valid in order to capture carbon more in general.
Why do you want to study atomically thin materials?
Atomically thin materials are very interesting. They can be synthesized using a variety of techniques spanning from chemical vapor deposition, pulsed laser deposition, molecular green epitaxy, and so on. And it is extremely important to study them because materials, when they are reduced down to the nanoscale, so when the thickness of the material is some atoms, or even in the extreme case, one atom, the material can exhibit properties that are completely different from the bulk material. And so, for example, its physical, optical, electrical properties can be properties that are not predicted for the bulk material that we use every day, for example. Think, for example, to graphene, which is a layer of graphene is an atomically thin material, but this is not the only case. These materials can be used, for example, in thin film transistors, in electronics, in the realization of optical devices, and most of these materials, if they are produced in a proper way, show properties that can be controlled and that can depend, for example, of the number of layers. So the same material can exhibit properties that are completely different, not only from the bulk phase, but also, for example, if we have 1, 2, or 3 layers of the same material, we can change, for example, the optical emission, the band gap of the material, and so on. And so if we want to apply these materials, for example, in an electronic device, fundamental to know how these materials and these properties are.
What are theranostic nanoparticles?
They are nanoparticles which can be used for to diagnose something, but also with a therapeutic effect. We had this event with a professor from Torino. Her research group was studying these nanostructures, which basically were nanoparticles made of different shells. So we have an internal core made of metal oxide, and then an external layer made of a lipid membrane, which was functionalized with other molecules, so that these nanostructures were able to detect precise particles, like precise cells in the human body. In this case, they were basically cancer cells. How to make them? It's, I think, a very difficult process. It's a research thing. We are not allowed to perfectly know, but basically you have to make, first you make the shell, then you try to put a second layer, then you functionalize it. So I think also it's a very long process because you have to test the stability of the particle in each step. So you have to test, is this metal oxide stable? Put the lipid membrane on it, and you have to verify that the lipid membrane will stay attached to the nanoparticle, and which can be also used inside the human body. So it has to be stable inside the human body for a certain amount of time. You have to verify the precise reaction with the cells that you want. So it's not that we know precisely how to make this particle. She obviously didn't reveal her secrets to us, but that's mainly, I think, roughly the process?
The thing is that the process to obtain this particle is always very, very long and very complicated. So there are many phases and very complicated technologies behind this. So it's not an easy task to answer this question. It would take a very long time, and also researchers need like years and years of practice and research in order to obtain these particles and later to functionalize them.
How can nanotechnologies be used for rockets?
This field of application of nanotechnologies is probably the most advanced one, meaning that research here is still ongoing with respect to other fields, like for example, biology or energy, where we already have some implemented applications of nanotechnologies. For example, in the event that we held last year about this topic, we saw that aluminum nanoparticles in particular can be used in the fuels of rockets. The main reason is that in this way, we are able to lower the total weight of the rocket, which of course is a big plus. And at the same time, we are also able to increase the energy that we obtain from the combustion of the fuel. This is the main trend, let's say. We can use nanoparticles in the active fuel so that we can obtain more energy with the same amount of fuel, and at the same time, the rocket itself, since the fuel is less heavy, of course, the rocket will be less heavy, so its motion will be easier to obtain, basically.